All right, welcome to Online Calculus 2. This is a very special video. Notice I'm coming to you live from outer space. Let's go ahead and get started. Pull up what we'll be working through. Okay, and in this video, we're going to be learning about a topic called improper integrals. Now, what this builds off of is a familiar idea of integrals, kind of coming out of Calc 1 and 2. We were first introduced as integrals as area. So we think area beneath the curve. We can calculate that area by evaluating an integral from a to b for that function. All right, well, that's pretty much been every integral we've encountered so far in Calc 2. It has been what we'll say is finite. So in other words, it's finitely long and finitely tall. So the length, the interval, is finite, a to b, and then the height, represented by the function values, was finite as well. All right, so we're going to make a change. What instead of the region being finite, what if it's infinite? And that could happen in two ways. Maybe the region is infinitely long, and we have maybe three different types of intervals there: a to infinity, negative infinity to some number a, or the full x-axis, negative infinity to infinity. The other possibility for how a region could be infinite is if the function value becomes infinitely tall. And that's usually due to there being some sort of vertical asymptote. So let's take a look at just some standard examples that we're going to learn about and be able to evaluate eventually. All right, we have three of them here. The first one is of relevance to what you might be getting to after this course, with what's called the normal distribution coming from statistics. This is also known as the bell curve. It's given by a simple equation, e to the negative x squared. And in statistics, you might be interested in the basically the total probability. And in some way, it's related to this integral from negative infinity to infinity of that function e to the negative x squared. Now, there's two more there, the graphs of 1 over x and the graph of e to the negative x. And we might ask for 1 over x, what is the integral from 1 to infinity? And for e to the negative x, what is the integral from 0 to infinity? Now, the reason why you might want to have some mathematical tools available is notice how I sketched each of those by hand. The two regions, the second and third, look very similar. Now, they're going to have very different behavior, as we'll see in some examples. It might work out that regions that are infinitely long could have infinite area. And for mathematical reasons, an infinitely long region might actually have finite area. All right, so we're going to kind of split these topics into two parts. The first part in this video will be addressing what improper integrals are, and there's two standard types. The second part, something called the comparison test, we're going to save that for a follow-up video right after this. All right, so let's get started with the first part. Let's say we were trying to define an integral from 0 to infinity for some function f of x, and we just have a representative graph right there of some possible function. Now, we can't actually integrate from 0 to infinity. Remember, integrals are adding up small pieces. There's no way we can add up all the small pieces from 0 to infinity. So the way we get around this is we integrate from 0 up to some number t, and we're going to kind of find a way to introduce limits. Now, any place you're dealing with infinity within the calc sequence, limits likely come into it. So what we do in this scenario is we integrate from 0 to t, and then we're going to take a limit as t goes to infinity. All right, so we have the basic setup down there. The integral from 0 to infinity, we're going to split that into two parts. We're first going to evaluate the integral from 0 to t. And once we've done that, we'll evaluate the limit as t goes to infinity. All right, now this first type that we have a sample graph above is what we're going to call a type 1 improper integral, where the region is infinitely long. That could occur as one of two types, a number to infinity, or maybe negative infinity to a number b. All right, both of them, how we handle them is we replace the infinite part in the integral with some variable t, and then take a limit as t either approaches infinity, or in the second version, we take a limit as t approaches negative infinity. All right, there's two terms introduced. You might recall from Calc 1 that some limits do not exist. And since we're setting up these improper integrals as limits, these improper integrals might not exist. So the two terms we introduce are improper integral could converge. That is the case where the limit that we're introducing exists. If the limit does not exist, then we say the improper integral diverges. Now these terms are being introduced for the first time. Kind of intuitively, what converge means, or the idea of convergence for an improper integral, is that the area is finite. The second part, a divergent improper integral, or if we say an improper integral diverges, that basically means the area is infinite. All right, so let's jump into some examples. Example 1 here is going to ask us to evaluate each improper integral, and then we'll determine if the improper integral is convergent or divergent. All right, let's go through part A together, and then I'll turn it over to you for parts B and C. So for part A, the first way we're going to approach this is we take the improper integral from 1 to infinity, and we replace the infinity with some variable t, and then take a limit as t goes to infinity. All right, we're going to split this into two parts. First, we're going to evaluate that integral from 1 to t of 1 over x squared. Now, this is pretty straightforward. You can rewrite 1 over x squared as x to the negative second power, and then you can apply the basic power rule to that to integrate it. You should find you get as your antiderivative negative 1 over x, and if we plug in our limits, x equals t and x equals 1, subtracting using the fundamental theorem of calculus, we should get this expression negative 1 over t plus 1. So that's basically the first step for improper integrals. We evaluate the integral. Now we can take the limit of that expression as t goes to infinity. Now, if you recall some things about limits from your Calc 1 course, you might recall kind of the be-all, end-all for limits, Lhopitals Rule. We're going to see that come up in a later example. But for this one, notice the quantity we're evaluating the limit of. We have a reciprocal 1 over t, and t is approaching infinity. Now, when you have 1 over a increasingly bigger quantity, that fraction as a whole will get smaller. The 1 over t part is going to approach 0 as t approaches infinity. We're not replacing that expression with 0, but in the limit as t goes to infinity, it'll get closer to 0. Okay, the whole thing leaves us then with the limit is approaching 1. And we say in that case, since the limit here exists, that this improper integral from 1 to infinity of 1 over x squared is convergent, since we got basically a finite limit value there of 1. Okay, what that means is that area represented graphically there is finite, since we got a convergent improper integral. So keep in mind, convergent improper integrals intuitively mean the area beneath that curve is finite. All right, so at this point, you might want to pause the video so that way you can have an attempt at evaluating parts B and C. Check back in a few minutes, and we'll go through parts B and C and continue. Welcome back. Let's go to part B, the improper integral from 1 to infinity of 1 over x. So same thing, we can replace the infinity with t, and then evaluate the limit as t approaches infinity. Now this antiderivative is a little bit simpler. We don't need any fancy integration methods. 1 over x has a simple antiderivative, natural log of x. Now you might recall from your pre-calc course, natural log of 1 equals 0. That's because e to the 0 equals 1. Remember, logs and exponentials are inverses. This expression just evaluates down to natural log of t. Now this might be a little bit tricky to then evaluate the limit as t goes to infinity for natural log of t, unless you're very familiar with basically the graph of natural log and some of its properties. So let's introduce that, maybe review that. We have our basic graph of natural log of x, and notice as you continue going further to the right, that's as x is approaching infinity, the graph keeps getting bigger and going up. So what that means is the limit for natural log of x as x approaches infinity, while that approaches infinity, that means that limit does not exist. Recall from Calc 1, limits exist when the quantity approaches a single finite value. So what we find here is the limit as t approaches infinity of natural log of t is infinite, it doesn't exist, which means this improper integral from 1 to infinity of 1 over x is divergent. And what that would basically mean is for the graph of 1 over x, the integral from 1 to infinity, the area beneath that curve is now infinite. All right, if we go to the last one for part C, same thing, we can replace the infinity with t, and then evaluate a limit as t goes to infinity. Now this one, you can make quick work of it if you recall your 1 over a shortcut, saving you a little bit of time for maybe doing a u substitution. So here, for this integral, our a value, what's multiplying x, is -1. So if you use your 1 over a shortcut here, you'll find your antiderivative is negative e to the negative x. We're going to evaluate that from x equals 0 to x equals t. That's plugging in our limits from the fundamental theorem of calculus. And if you do that, the e to the 0 part will give you 1. There's some negatives that cancel out. And we're left with, for the integral, 1 minus e to the negative t. Now, like the previous example, it's good to keep some basic graphs in mind, especially exponential functions. And notice for your graph of e to the negative x, as you go very far to the right towards positive infinity, the y values get closer to the horizontal asymptote, y equals 0. All right, what that means for this problem is that the e to the negative t part, that approaches 0 as t approaches infinity. And what we're left with here is the whole limit for that quantity is approaching 1. All right, and since we got a limit that exists, we say that improper integral is convergent, meaning the area beneath that curve from 0 to infinity is finite. Notice all the graphs we've looked at here. By hand, they all look very similar. Some of them have represented finite area, like this one. The previous example, part B, while the graph sketched by hand looks similar, it represented infinite area. All right, so at this point, we're going to introduce an important quantity, something called the p integral. Basically, our previous examples, parts A and B, fit this pattern where we're integrating 1 over a power of x. So our function here is 1 over x to the p, and we integrate that from 1 to infinity. I encourage you to try to evaluate this, maybe as a general antiderivative. Maybe rewrite that as x to the negative p, and you can apply the power rule to find the antiderivative. If you do that, you'll find that there's two possibilities. If p is greater than 1, you actually get a number here for that improper integral, 1 over p minus 1, where p is that reciprocal power of x. The second possibility you get for this integral is if the values of p are equal or less than 1, the improper integral is divergent. All right, so if we review the previous two examples, parts A and B, example 1a was the case where the power p was 2. Our function was 1 over x squared. Since 2 is greater than 1, that's a convergent integral by our p integral test. Example 1b is where the p value, the power, is 1 over x. Since the value for p equals 1 in this case, this is divergent by the above p integral. All right, now one thing we'll be getting to in the follow-up video, kind of the second part to this online lecture, is something called the comparison test. And this quantity called the p integral is going to play a central role in that. So maybe copy this down into your notes for reference before you move on to the follow-up video for part 2 for the comparison test for improper integrals. All right, let's take a look at a more complicated example. This one will kind of recall a lot of properties and formulas and such from your Calc 1 course, maybe even going back to pre-calc. And the question is going to ask, determine if this improper integral from negative infinity to infinity of 1 divided by 1 plus x squared, determine if that is convergent or divergent. Now, this one's a little bit tricky. I want to give you some suggestions before you try it. You could approach this with two different options here. One option is, while this is a improper integral, there's infinities in the limits. It's a doubly infinite improper integral. It goes from negative infinity to infinity. So we could split this up from negative infinity to 0, and then another integral from 0 to infinity. And now we have two type 1 improper integrals. And we could evaluate them kind of similarly to what we did in example 1, replacing the infinities with t, and then taking respective limits as t approaches negative infinity, and the second integral as t approaches positive infinity. Now that will work, but notice you have two integrals to deal with rather than one. The second option, which is a little bit more efficient, is to notice we have a symmetric interval from negative a to a. Here it's from negative infinity to infinity. And the function we're integrating is even. You might recall an even function is one in which you plug in negative x. You get the same thing as if you just plugged x into that function. A quick shortcut is if the function contains, basically I'll say only even powers. And our function 1 over 1 plus x squared does only contain even powers. All right, what this allows us to do, this was back when we introduced U substitution that we first saw this property. We can double the integral from 0 to a. Here, we're doubling the integral from 0 to infinity. All right, and this is a little bit more efficient than the first option, since now we only have one improper integral to deal with. All right, we're going to again replace the infinite limit up there in the integral with t, and then evaluate a limit as t approaches infinity. Now the actual antiderivative, like the previous example for part B, 1 over x had a basic antiderivative. 1 divided by 1 plus x squared also has a basic antiderivative. It's inverse tangent. So this is kind of hopefully an antiderivative that you remember. We're going to plug in x equals 0 and x equals t and subtract there. You might recall inverse tangent of 0 equals 0. That's because tangent of 0 equals 0. And that whole integral just evaluates to inverse tangent of t. All right, now we evaluate that limit, and this is where it gets a little bit tricky. Probably if you're not familiar with the kind of the graph of inverse tangent. So let's recall that graph. Pops up enough places in the calc sequence, it's good to know. All right, and notice here it has two horizontal asymptotes. An asymptote as you go far to the right as y equals pi over 2. And then as you go very far to the left towards negative infinity, there's a different horizontal asymptote, y equals negative pi over 2. All right, now we're of interest here taking the limit as t approaches positive infinity. And if you basically look at that graph as you go very far to the right, the function values get close to pi over 2. So the limit for inverse tangent of t as t approaches infinity, that limit is just pi over 2. And if we multiply by that factor of 2 out front, we find that this whole improper integral evaluates to pi. And since that limit exists here, we get a finite number. That means this improper integral is convergent. All right, before we get to kind of a follow-up example, this is going to be a good time to review what Lhopitals Rule is. If you say Lhospital, I will fail you. Remember, Lhopitals. All right, Lhopitals Rule deals with limits with indeterminate forms, either 0 over 0 or infinity over infinity. Now you have to have the function defined as a fraction, f of x over g of x. And what Lhopitals Rule allows you to do, provided you have an indeterminate form, is evaluate the same limit, but for f prime of x divided by g prime of x. Hopefully you remember to be careful to not apply the quotient rule here. Lhopitals Rule is just the derivative of the numerator divided by the derivative of the denominator for the function you're evaluating the limit of. Okay, so let me give you an attempt at example 3. This one's going to be a little bit trickier. It's a little longer. At some point through the problem, once you are down to evaluating the limit, you're going to have to use Lhopitals Rule. So at this point, maybe pause the video, give this one an attempt. I'll give you a hint. The antiderivative requires integration by parts. So pause the video and we'll check back in a few minutes. All right, welcome back. The first thing we want to do for this one is get the integration out of the way. There's a little bit of work involved. All right, the work is just integration by parts. We're going to choose our u as x and our dv as e to the negative x dx. All right, notice in your calculation of v, you have your 1 over a shortcut appearing again, like we saw in a previous example in this video. Your antiderivative for v comes out to negative e to the negative x. And if you combine all the pieces together with your integration by parts formula, evaluate the remaining integral of v du, you should find that factoring out the exponential, you can get this expression for your antiderivative, negative, and then the quantity x plus 1 times e to the negative x. All right, now that's basically the hard part for this example. We can put the limits on there for the integral sign, 0 to infinity. And since this is an improper integral, we can replace the infinity with t. All right, we already did the hard work of integrating by parts to find that antiderivative. The only thing we need to do at the end here is plug in x is t, and then separately x equals 0, and then subtract. That negative that we have out front there is going to be a little bit tricky, so just be careful with subtracting a negative. And if you're careful of that, you should find you get at the end here, just plugging in your limits, it should evaluate to 1, and then minus the quantity t plus 1 times e to the negative t. All right, it is that integral, or sorry, that limit for the last part, t plus 1 times e to the negative t. That's where we're going to want to apply Lhopitals rule. As written, t plus 1 times e to the negative t, the t plus 1 part gets bigger towards infinity, but the e to the negative t gets smaller towards 0. So we do get an indeterminate form here. The indeterminate form is infinity times 0, but Lhopitals rule only applies to 0 over 0 or infinity over infinity. We can easily rewrite that. Notice the negative exponential, e to the negative t, a negative exponent, you can flip that into the denominator. At this point, we now have a fraction, and we can apply Lhopitals rule, differentiating numerator and denominator individually. All right, here the variable is t, so we're going to be differentiating numerator and denominator with respect to t, and the derivatives are rather simple. The numerator differentiates to 1, and then the denominator differentiates to e to the t. All right, that integral, or that limit at the end there, doesn't require anything fancy. It's of the form 1 over a big quantity. And as t approaches infinity, that denominator gets bigger and bigger. So 1 over a big quantity gets small. As t approaches infinity, that expression 1 over e to the t is going to approach 0. It's going to get as small as possible. All right, now if we use that in the previous step right above there, it is the last part in that limit, the t plus 1 times e to the negative t. Lhopitals rule showed us that that approaches 0 as t goes to infinity. So this whole thing, that whole limit there, notice there's the 1 in front. That whole limit will approach 1. So in this case, since that limit exists and it approaches a single finite number, 1, we say that improper integral is convergent. Intuitively, what that means is the area beneath the graph of that function from 0 to infinity is a finite area. All right, the last part of our video and online lecture deals with the second type of improper integrals. This we call creatively type 2. And this deals with, instead of the region being infinitely long, it might be the case that the region is infinitely tall. And this is usually due to the function having a vertical asymptote. The technical term we call that in calculus is an infinite discontinuity, somewhere in the interval you're integrating over. All right, so let's take a look at 2 sketches to understand the setup here. We might have it be the case where from A to B, that there's a vertical asymptote at the left endpoint A, or it could be maybe there's a vertical asymptote at the right endpoint B, like in that second graph. The main idea with improper integrals is wherever the infinity occurs, we replace it with a variable and then take a limit as we get closer to that value. Earlier, we were taking a limit as t gets closer to infinity or negative infinity. Here, we'll be taking limits as t gets closer to A or B from either the left or right sides. All right, so in the first case where the vertical asymptote is all the way on the left at x equals a, we replace the lower value of the integral, a, we replace that with a variable t, and then we'll take a limit as t approaches a, but only from the right side. Notice in the sketch, the interval from A to B, in order for us to stay in that interval, we can only approach A from the right side. The second graph, where the vertical asymptote is all the way on the right side, we're going to replace now the upper value for the integral B with t, and then we'll take a limit as t approaches B, and to stay in the interval, we're going to let the values of t approach B from the left side. You might recall one-sided limits from your Calc 1 course. We indicate the right or left side there with a little plus or minus after the numerical value that you're approaching. All right, now before we get to examples, these ones are a little bit harder to identify. What we called type 1 improper integrals. There's always some sort of infinity in the integral sign, either an integral from 0 to infinity or something of that form. So you can see the infinity. For these ones that we're calling type 2, you might want to try plugging in the endpoints, x equals a and x equals b, plugging them into the function to see if it becomes undefined. Almost always, the simple functions we encounter in the calculus sequence, if there's an undefined function value, there's almost always a vertical asymptote in the graph at that x value. All right, let's move on to our last example for this, this part 1 of this video. So we're going to look at evaluating a type 2 improper integral. And notice here in the integral sign, you have the lower and upper limit as 2 and 5. So there's no infinities here. Hopefully you can see why this one is an improper integral. If you were to plug 2 into that function, the f of x, the function here, is 1 over the square root of x minus 2. If you plug 2 in, you're left with division by 0, which is undefined. So we know there's a problem with the lower value for the integral, or the lower limit, x equals 2. So we're going to replace that lower limit with a variable t, and then we'll take a limit as t approaches 2 from the right side. All right, a good first step is to always evaluate the integral. This one we can do with a combination of basic u substitution and changing the limits. So we might choose u as x minus 2. And then we can change our limits with our substitution and get our u limits as t minus 2 to 3. If you translate your integral from x to u, you arrive at this. To do the integration, you can rewrite 1 over square root of u as u to the negative 1/2 power. At this point, should be very straightforward to apply the power rule. We've seen that antiderivative through numerous examples in our previous face-to-face lectures. So you should find that integrates to 2 times u to the positive 1/2, applying the power rule for antiderivatives. Then we just plug in our new u limits, u equals 3 and u equals t minus 2. All right, think that the 1/2 power is a square root. Notice I rewrote the 1/2 powers as square root signs since they're a little bit more familiar and easier to work with. And if we go back to our integral up there, we evaluated the integral, now we can evaluate the limit. And if we take a limit for that expression as t approaches 2 from the right, some limits you can just evaluate them by plugging in. In this case, if you plug in t as 2, you'll find that square root term will approach 0 as t approaches 2 from the right. Notice why we're taking a limit as t approaches 2 from the right side. The t values here are bigger than 2. Had we allowed for approaching 2 from the left side, the values of t would be less than 2, and we would end up with a negative inside that square root. When you have negatives inside square roots, that gives you imaginary and complex numbers, which we're trying to avoid. So if we stick with a right side limit only as t approaches 2, we avoid that possibility. Okay, so that last term, the square root part, approaches 0. The whole limit then approaches 2 times square root of 3. And since that is a limit that exists, it's a finite number, we find that this improper integral is convergent. All right, before you move on to the second part, in the follow-up video, make sure to go back and review what you find that you need to from this video, from the 2 types of improper integrals, before moving on to the next topic called the comparison test for improper integrals.